The second type of passive process is osmosis. Osmosis, by definition, is the net movement of water from regions of high concentration to low concentration. Now, be careful with this definition as it's written here. It's regions of high concentration of water to low concentrations of water. So again, everything wants to go from high concentration to low concentration. And the reason, or the last part of this definition that's important to pay attention to, is selectively permeable membrane. What this means is that that membrane is only permeable to certain things. When that happens, that means those things, those solutes, cannot move. And so it's dependent on water to evenly distribute those molecules. So when the molecules themselves can't move because the membrane won't let them, water may move to help them equally distribute themselves. We can see this in this figure here, where we have some solutes. So basically solutes are the things that get dissolved, if you will. Water acts as a solvent. It is the dissolver. So you have this flask with a semi-permeable membrane, meaning it won't let these larger molecules, which are green and red, it won't let these leave. So there's a high concentration of these molecules in this flask. And you place this in a beaker of water. So water can go through the membrane because it's a semi-permeable membrane, not allowing the solvents out, or the solutes, but allowing the solvent in. The water can go in, but those cannot go out. And so when you place that, and in this example, it's a 3% salt solution, put that salt solution with the membrane down in the water in the beaker, then suddenly you have a situation in which these molecules want to be equally distributed, these salt molecules, but they can't leave. So they can't put space between themselves. And this is where water can come in and actually help, because it can diffuse across the membrane and it can come in. And what we see is it almost looks like it's defying the laws of gravity, because we'll see this liquid go up the column. And it's because water is coming in and it is helping separate or distribute those molecules that cannot leave this concentrated situation. So water will diffuse when we take this example in the lab and we talk about it in terms of humans. Water does diffuse through plasma membranes, those phospholipid bilayers. So water does move through osmosis when molecules cannot. The other way that water can quickly go across the membrane is through special channels that sometimes are produced or placed in the membrane called aquaporins. These aquaporins are specifically meant just for water, and you can find them most commonly in the kidney when we need to control how much water is being reabsorbed or released into the urine. Some terms that I think are important for you to know is when we're comparing the solutions on either side of the permeable or semi-permeable, membrane. So if this were the inside, well, this is the inside here, inside this funnel, and here's the semi-permeable membrane. When water comes in and is able to separate those molecules, and then let's say some of them were able to get out, these two solutions would be called isoosmotic. Iso means same. They have the same osmolarity. So two solutions with the same osmolarity across the semi-permeable membrane are called isoosmotic. Hyperosmotic is when one solution has more or higher osmolarity than the other. And an example here is this salt solution is hyperosmotic to the water in the beaker. And it's always a comparative term. When we talk about hypoosmotic, it is a solution that is less osmotic, has less osmolarity compared to another solution. So in this instance, water is hypoosmotic. It has less solutes in it. In fact, none. Hypoosmotic to the salt solution. Okay? And so those terms are really important, especially when we talk about the next thing. And that is tonicity. So we look at the tonicity of a cell because we have these semi-permeable membranes surrounding these cells, controlling what enters and exits a cell. So tonicity, how much of a solution is in a cell, is going to affect osmosis. If you have a hyperosmotic solution inside a cell, water wants to come in. It wants to help distribute those molecules. And so, as it says here, this is going to be used a lot of times when we're talking about solutes that cannot leave the cell. So if there's a higher concentration inside the cell of solutes, so ICF, intracellular fluid, and I use the brackets to indicate concentration, is greater than the extracellular fluid, then water will want to move into the cell. So water will want to go in. It wants in. All right, and this is into the cell. So when we talk about, again, we have those three prefixes, iso, hyper, and hypo. Iso meaning same, hyper meaning more, hypo meaning less. So if you place a cell, and we're using red blood cells here as an example, if you place a cell in a solution and it's got the same concentration of solute, then it will stay happy. So here we have in the middle a red blood cell that is placed in a solution that is isotonic. It has the same solute concentration. I don't know why I keep mixing those up, as the solution around it. And so there's no net movement, water in or out, and the cell's happy. Now, if you place that cell in a hypertonic solution, where this solution is more concentrated with solutes than in the cell, then the water in the cell is going to want to leave and try to separate these molecules. It's like, oh wait, I can help take care of my outside environment. When it does that, the cell loses water and it shrinks. And a formal term for that we call crenation, especially in red blood cells. In a hypotonic environment, this is where the environment or the solution has fewer solutes than in the cell. So just a couple, all right? And so that means there's more stuff inside the cell. And so again, water wants to rush in and help distribute, but it can be such a large difference that so much water can go inside the cause it to burst. And we call this lysis.